Hi, Sir Eldon Calamba here. Welcome to another video lecture series for General Physics 2. I hope you have your notebook, your pen, your calculator, and snacks with you. Let's start. So once again, this is Sir Eldon. We will be having Basic Electronics Part 2. Our goals for this video lecture series is to draw circuit diagrams with power sources such as cell or a battery, switches, lamps, resistors, fixed and variable, fuses, ammeters, and voltmeters. Evaluate the equivalent resistance, circuit, and voltage in a given network of resistors connected in series and or parallel or in combination. Given an EMF source connected to a resistor, we have to determine the power supplied or dissipated in each element in a given circuit. And lastly, we have to solve problems involving the calculations of currents and potential differences in circuit consisting of batteries and resistors. Electronics played a vital role in today's modern world. Now that we are in a pandemic, online transactions are preferred. Electronics is one of the products that has been derived by understanding electricity and magnetisms of physics. For this video lecture series, we will explore more on the applications of electricity and magnetism, specifically DC circuits. Even if our world has been running using alternating current or AC power sources, the methods and concepts in DC circuits can still be used in understanding AC circuits. And we have digital multimeters. A multimeter is a measuring device usually used in fabricating or troubleshooting some of our electronic devices. It is widely used by engineers and technicians. It is the same as diagnosing a patient wherein you must do some series of tests. For easy usage, we will be making use of digital multimeter. It is used for measuring voltage, current, or resistance in any circuit. All digital multimeters have numerical readouts that display the values of voltage, current, and resistance. The meter leads are color-coded. The black lead is connected to the common ground of the circuit and of the meter. The red one is connected to the slot depending on what is to be measured. Sometimes, some people refer to the red lead as positive and the black lead as the negative terminal. Please refer to the suggested video in Dagler, that is Beauty and the Bolt's discussion on how to use a digital multimeter. Please view it so that we could know on how to measure the current that is passing through a circuit, the voltage across a circuit element or across our resistor, and on how to measure resistances. There's a bonus there on how to make sure that our circuit is having no issues when it comes to open circuit. That is your connectivity. Let's now talk about the different circuit configurations. We have the series circuit configuration, parallel circuit configuration, and the combination, that is the series parallel circuit configuration. Let's start with the simplest one, and that is the series circuit configuration. If a circuit is in series circuit configuration, it provides only one path for current to flow, wherein all of our charges will just flow in one path, in one straight path, or in one loop. In the figure as shown, it shows two resistors that are connected end-to-end with their opposite ends connected across the terminals of a voltage source. An electric current is the movement of charges between 2 points, from higher potential to lower potential, when components in successive order, as in our figure, they form a series circuit. The battery supplies the potential difference that forces our charges to flow from the voltage source going to R1 to R2 and then going back to the voltage source. It should be a closed loop. So the current passing through each resistor is just the same. So meaning to say, the current passing through R1 and R2, that is I1 and I2, they are just equal to the total current that is passing through our circuit. In solving for the total current passing through our circuit, it is right for us to solve for the total resistance. The total resistance for a series circuit configuration is very simple to get, and that is we just have to add all the resistances, that is R1 plus R2. And if you have multiple resistors that are in series, so that is just the total resistance is just equal to R1 plus R2 plus R3 and so on and so forth, as shown in this equation. So if you have n number of resistors, then you have to add n number of resistors to get the total resistor or the total resistance. Then you have to substitute that one to Ohm's law to get the total amount of current passing through our circuit. For the voltage drop across each resistor, it will be a different story. Since the current is just the same, the voltage drop will be different because they have different values for resistances. So if R1 and R2 has voltage drop, they will be not equal to each other. So it will depend on the value of our resistor R1 and R2. And that is still using our Ohm's law, wherein Vn is just equal to IT times Rn. Or if you want, V1 is equal to I1 times R1 and V2 is equal to I2 R2. Let's have an example. A simple example. Example number 1. Calculate for the total resistance of the given circuit. Given that R1 is 1 kilo ohm, R2 is equal to 20 kilo ohms, R3 is equal to 10 kilo ohms, and R4 is equal to 10 kilo ohms. We now have this circuit configuration. We have our voltage supply and then our 4 resistors. For all we know that this circuit belongs to a series circuit configuration because the ends of our R1, R2, R3, R4 are connected together and the end of R1 and R4 is connected across our voltage source. So it will provide one way or one flow of current. In order for us to get for the total resistance, we have to open our circuit through our power supply, through our voltage supply. So it is as if we have to cut the wires here and then we have an open circuit. It is as if we have a multimeter, what is the reading what is the resistance reading at this point, across this point, wherein it will read R1, R2, R3, and R4 all together. So since this is series, we have to open this. So let's open this one. So you now have this. So what would be the reading here? The total resistance. So that is very easy. R1 plus R2 plus R3 plus R4. And take note, the values of our resistors, they are all in kilo ohms. Let's go back. This is kilo ohms, R1, R2, R3, and R4. They are all in kilo ohms. So meaning to say, we have to convert first it to ohms. And using unit prefixes, we have times 10 raised to 3 for kilo. So you have here now, in the solution, R1 plus R2 plus R3 and plus R4, you have 1 times 10 raised to 3 ohms, plus 20 times 10 raised to 3 ohms, plus 10 times 10 raised to 3 ohms, plus 10 times 10 raised to 3 ohms. We now have 41,000. We could actually have this one, 41,000, or we could translate it better. We have 41 times 10 raised to 3 ohm, or we have 41 kilo ohms. So this is now our final answer. Let's have example number 2. Let's deal now with current and with the voltage supply. Example number 2. In the given circuit, solve for the following. The total current passing through the circuit IT, the current passing through each of the resistor I1, I2, I3, and I4, and lastly, the voltage drop across each resistor, wherein we have V1, V2, V3, and V4. Still, this is a series circuit configuration. In order for us to get for the total current, that's actually the step 1, we have to open our circuit through the voltage supply. So, open our circuit and then we have to get the total current. So that is R1 plus R2 plus R3 plus R4. So that is 1 times 10 raised to 3 ohms plus 200 plus 600 ohms plus 300 ohms. You now have the total resistance, that is 2,100 ohms, or you could have 2.1 kilo ohms. But I am not yet done solving, so I will just express it in terms of ohms. We could now answer letter A. We bring back our voltage supply and connect it across to our total resistance. We could represent our R1, R2, R3, R4 as one resistor only, and that is RT. So we now have IT that is just equal to the voltage source over the total resistance. So you have 12 volts over 2,100 ohms. We now have a total current of 5.714 times 10 raised to negative 3 amperes, or that's very small, that's times 10 raised to negative 3, that is milli. Using unit prefixes, we now have the total current that is equal to 5.714 milliamperes. So that is our answer for letter A. Let's have letter B. We are asked about the current. Let's now have letter B. We are asked about the current passing through each resistor. So since this is just a series circuit, if we're going to break down our total resistance, it's just equivalent to R1 plus R2 plus R3 and plus R4. and they are in series, they will experience the same amount of current. So meaning to say, the total current will be the same current that is passing through R1, R2, R3, and R4. If we got our total current as 5.714 milliamperes, then that is our value for our I1, I2, I3, and I4. And please don't forget about that one, wherein if it is a series circuit or if your resistors are in series, they will experience the same amount of current. But then it will be a different story for our voltages across each resistor. Since we are asked about that voltage, we now have letter C. We are asked about V1, V2, V3, and V4. Simple Ohm's law from V is equal to IR. Since we have to get for V1, that is I1, R1, V2, I2, R2, V3, I3, R3, V4, I4, R4. So for V1, we got 5.714 volts, V2, 1.143 volts, V3, 3.428 volts, and V4, 1.714 volts. Here's a trick. How will you know if your answer is correct? You add your V1, V2, V3, and V4 all together. It will be approximately equal to our Vs, wherein this is approximately equal to 12 volts. And that's what we call our Kirchhoff's voltage law. More of that when you go to your basic electronics or when you go to circuit theories. Let's now talk about parallel circuit configuration. In a parallel circuit configuration, it is as if your current from your voltage source is being split into several current or several branches, because you have your resistance R1 and R2 and so on and so forth that are connected across each other and across our voltage source. A parallel circuit configuration provides one common voltage across all our components. So every component across that voltage source provides a separate path or branch for current to flow. The individual branch currents are calculated using Ohm's law, where VA is just, or your Vs is just equal to the applied voltage, and R is the individual branch resistances. So the total current supplied by the voltage must be equal to the sum of all the branch currents. A parallel circuit is formed when two or more components, for our case, resistors, are connected across a voltage source, as shown. R1 and R2 are in parallel with our voltage source. The terminals of these resistors are directly connected to the positive and negative terminals of the battery. With this, the voltage across each resistor must be the same of the battery. Parallel circuit configurations are used actually to connect components that require the same amount of voltage. Most common application of a parallel configuration is the typical house wiring to the power line. With many lines and appliances connected across the 220 volt source, the wall receptacle has a potential difference of 220 volts across each pair of terminals. Therefore, any resistance connected or appliances connected to these receptacles will always have a 220 volts. Now, by inspection, since we already know that the voltage across each these resistances are just the same, meaning to say V1 and V2 is just equal to our voltage source, Vs. So meaning to say also, if we will connect multiple resistors that are in parallel with this voltage source, it will still be equal to our voltage source. And solving for the current, we will just go to Ohm's law again. So that is IN is equal to Vn over Rn. Think about it like this. If series current will have the same current passing through all the resistances, for parallel circuit configuration, it will have the same voltage but different currents passing through each resistor. Same thing with our series circuit configuration. We could represent these parallel resistors as one resistor, as one big resistor, actually it's one small resistor, because the value for this equivalent resistance is actually smaller than the least resistor that is present in our circuit. If you have the least resistance that is equal to 10 ohms, then the equivalent resistance will be smaller than or lesser than 10 ohms. So in solving for the equivalent resistance, it will have a different formula now. I will call it as the equivalent resistance. In getting for the equivalent resistance, it is just equal to 1 over 1 over R1 plus 1 over R2 plus 1 over Rn, or and so on and so forth if you have multiple resistances. Sometimes I call this total resistance, but I like the term equivalent resistance so that I could just distinguish the two if it is a parallel circuit or a series circuit. But if I have the last configuration, I will just call it as equivalent resistance. So let's dive into a simple example. Example number 3, solve for the equivalent resistance of the circuit shown. So you have a voltage source that is in parallel with R1, R2, and R3. The values of our R1, R2, and R3 is equal to 1 kilo ohms, 800 ohms, and 1.5 kilo ohms respectively. Take note, you have their kilo ohms, R1 and R3. So you have to convert that first into ohms. So we use unit prefixes. So in getting for the equivalent resistance, that is just equal to 1 over 1 over R1 plus 1 over R2 plus 1 over R3. So that is 1 all over 1 over 1 times 10 raised to 3 ohms plus 1 over 800 ohms plus 1 over 1.5 times 10 raised to 3 ohms. So we now have an equivalent resistance of 342.9 ohms. Take note, it is lower than the least value of resistance in our circuit, and that is lower than 800 ohms. So we have an equivalent resistance of 342.9 ohms. Let's now have example number 4. In the given circuit, solve for the following. A. The total current passing through the circuit, IT. The voltage across each resistor V1, V2, V3, and V4. The current passing through each resistor I1, I2, I3, and I4. Given that we have our voltage supply that is equal to 15 volts, R1 1 kilo ohm, R2 900 ohms, R3 1.5 kilo ohms, and R4 1 kilo ohm. So we now have this circuit configuration wherein we have the voltage supply that is in between across R1, R2, R3, and R4. Before we could start solving for the total current, it is better to represent all our resistor as one resistor. So we have to get the equivalent resistance. So for us to get the equivalent resistance, we could open our circuit through the voltage supply. So as we all know, we could actually rearrange this circuit wherein we could move this REQ towards the left side. And then we could move R1 and R2 to the right. So we could have this circuit configuration. And as we can see, R1, R2, R3, and R4 are just connected parallel to each other. So this is under parallel circuit configuration. So for us, we could easily get for the equivalent resistance. So that is 1 all over 1 over 1 times 10 raised to 3 ohm plus 1 over 900 ohms plus 1 over 1.5 times 10 raised to 3 ohm plus 1 over 1 times 10 raised to 3 ohms. Just take note, we have to express our resistance in terms of ohms. So you have your equivalent resistance now that is equal to 264.7 ohms. So we can now easily solve for letter A. We could now bring back our voltage supply. So we now have this one. So this is just in series. We could easily make use of our Ohm's law. So IT now is just equal to Vs over Req, that is 15 volts over 264.7 ohms, giving us the total current that is equal to 56.67 milliamperes. This is now our answer for letter A. Let's have letter B, wherein we have to solve for the voltage across each resistance. So across each R1, R2, R3, and R4. And it's very easy because this is just a parallel circuit configuration. Or if we could break down our REQ into 4 resistances, we now have this one. So you have R1, R2, R3, and R4 again. So since this is just a parallel circuit configuration, whatever the value of this voltage supply will just be equal to the voltage across R1, across R2, across R3, and across R4. So our voltage supply is 15 volts. Hence, our V1, V2, V3, and V4 is just equal to 15 volts. Letter C, we are asked about the current passing through each resistance, and that is your I1, I2, I3, and R4. And by Ohm's law, I1 or I is just equal to V over R. So I1 is just equal to V1 over R1. Same thing with I2, V2 over R2, I3, V3 over R3, I4, V4 over R4. So, since they are experiencing the same amount of voltage, we could have V1, V2, V3, and V4 equal to 15 volts. So, for I1, 15 volts over 1 times 10 raised to 3 ohms, we got 15 milliamperes. For I2, 15 volts over 900 ohms, we have 16.67 milliamperes. I3, we have 15 over 1.5 times 10 raised to 3. We have 10 milliamps. And I4, we have 15 volts over 1 times 10 raised to 3 ohms. We got I4 that is equal to 15 milliamps. Now, the question, how will you know if I got the correct current? So just like in series circuit, we have your Kirchhoff's voltage law. This time, we could actually have our another kind of Kirchhoff's, that is Kirchhoff's current law, wherein the total amount of current is just equal to the sum of your individual branch currents if it is in parallel. Meaning to say, if we will add up I1, I2, I3, and I4, it will be equal to our answer to our total current, and that is 56.67 milliamperes. So that's up to you to add this 15 milliamps plus 16.67 milliamps plus 10 milliamps plus 15 milliamps. It will be equal to our answer in letter A. So that's for example number 4. Let's now have the last configuration, and that is your series parallel configuration. A series parallel circuit configuration is usually called a combination circuit. A combination circuit uses different combinations of series and parallel connections. Some of the circuits that we use today are mostly series parallel circuit or series parallel combination circuit because we have different kind of gadgets that require different amounts of current, amount of voltage, and different points of their circuit. In general, series parallel or combination circuits are used when it is necessary to obtain different voltage and current values from a single voltage source. When analyzing combination circuits, the individual laws of series and parallel circuits can still be applied to produce much simpler overall circuit. So as you can see here with our illustration, you have your voltage supply and then you have several resistances. You have your R1, R2, R3, and R4. For us to analyze this better, we will still be using the idea of series and parallel circuit individually. We have to determine if our resistances are in series together or they are in parallel with each other. And what we're going to do here is that we have to deduce and deduce and deduce our circuit wherein it will become simpler. By the way, there's no fixed formula here. It will really depend if we have understood the concept in series and in parallel circuit. And then we just have to combine them all together. So let's go directly to an example. A simple example. Solve for the equivalent resistance of the circuit. Given that you have R1 500 ohms, R2 600 ohms, R3 900 ohms, R4 700 ohms, and R5 300 ohms. So you can see we have your voltage supply here. There's no definite answer if this is a series or parallel circuit, but this is actually a combinational circuit. So we have to deduce this circuit in order for us to get the equivalent resistance. Just like what we did with our series and in parallel circuit, wherein in order for us to get the equivalent resistances, we have to represent our several resistor as one equivalent or one total resistance or one total resistor. In order for us to get the equivalent resistance, we will have to open our circuit through our voltage supply and then we will work our way, wherein we will start from the farthest resistor, farthest from our open circuit, and that is at point R3. So open, so we will start with R3. With R3, our R2 is connected. R2 and R3 are connected in series configuration because their ends meet, and then the other end of R2 and R3 are connected across R4. R2 and R3 are in series configuration. So we could represent that one as RA first. So we could now have this kind of circuit. This is actually the equivalent circuit. So as you can see, it made our life kinda simple. So RA is this is just R2 plus R3, so that is 1500 ohms. Next is that we start now with RA. So RA is connected to R4. It is connected in parallel configuration because the ends of RA and R4 are connected together across each other. So meaning to say RA and R4 are in parallel. We could have that as RB. So RB now, it will become like this one because RA and R4 just combined together. This is just 1 over 1 over RA plus 1 over R4, giving us RB that is equal to 477.3 ohms. And lastly, we now have this much simpler circuit wherein R1, RB, and R5, it is just connected in series. So we could have that as our REQ now. So REQ is just equal to R1 plus RB plus R5. So that is 1277 ohms. This is now our equivalent resistance. So that's for example number 5. First is we open our circuit through our source. Next is in getting for the equivalent resistance, we start from the farthest resistor from the open circuit. Let's now have example number 6. For the given circuit, calculate for the following. A. The equivalent resistance of the circuit, REQ. B. The total current IT passing through the circuit. The current passing through each resistor, I1, I2, I3, I4. And lastly, the voltage across each resistor, that is V1, V2, V3, and V4. Given that Vs is equal to 12 volts, R1 is 5 ohms, R2 is 5 ohms, R3 is 3 ohms, and R4 is 1 ohm. This is a combinational circuit. It's a series parallel combination. First is we have to get for the equivalent resistance. So we have to open our circuit through our power source and then get the REQ. We start from the farthest resistor, and that is R2 and R4. So R2 and R4, we could have that as RA. They are in series together. So RA is just equal to R2 plus R4, giving us 6 ohms. Next is RA is in parallel with R3, giving us RB. So RB is just equal to 2 ohms. And then lastly, we have the REQ now, where in REQ, this is just R1 and RB because they are just in series together. So R1 plus RB is equal to our REQ, which give us 7 ohms. So for letter A, our answer is the REQ is equal to 7 ohms. Next, for letter B, we are asked to get for the total current. So IT, that is just equal to the voltage source over REQ. Vs, how can we have Vs? We have already opened our circuit. Then we have to bring back our Vs, our voltage supply. So for us to have a complete circuit, a closed loop circuit, so that's 12 divided by 7 ohms. Our total current now is equivalent to 1.714 ampere. Now in getting the current passing through each resistor, it will have a different method. So in letter A, we made our circuit simpler. We deduced it to this kind of circuit that we have in solving for letter B. Now we will work our way that is in opposite with letter A. We have to bring back or break down this REQ one by one. So we break down REQ. So in breaking down REQ, we bring back now R1 and RB so that we could solve for I1. So since this is still a series circuit, meaning to say the total current is just equivalent to the current passing through our R1. So I1 is just equal to I total. So I1 is just equal to 1.714 ampere. And then for V1, this is just Ohm's law. V1 is just equal to I1 R1. So that's 1.714 amperes times 5 ohms. So that is 8.570 volts. So that is your V1. That's the voltage across our R1. And by the way, letter C and letter D can be solved simultaneously actually. Because we have to find a way wherein we could solve the different current and the different voltages in our resistor. So let's focus now to RB. RB is in series with R1. So meaning to say, the current that is passing through that resistor RB is equivalent to 1.714 ampere. So we could get the voltage drop or we could get the voltage across RB. This is vital because it will pave the way for us to solve the voltage across R3.
So let's get VB first. So the voltage across our RB is just equal to IB RB. So that's 1.714 amperes times 2 ohms. So it will give us 3.428 volts. So since we got the VB already, this one, the voltage across our RB, we could break this RB into R3 and RA. And mind you, R3 and RA are in parallel with each other. Meaning to say, if we break down RB, the voltage across R3 and RA will just still be equal to VB. Hence, our V3 is just equal to 3.428 volts. So given that one, we now have our V3, we could actually solve now for the current passing through R3. And that is I3 equal to V3 over R3. So meaning to say, we could have now 3.428 volts over 3 ohms. So it will give us 1.143 amperes. So that is the current passing through our R3. Next is, let's focus with RA. We know the voltage across RA, and that is just equal to 3.428 volts because RA is in parallel with R3. So VA is just equal to VB, that is 3.428 volts. We could solve actually for the current passing through RA. So IA is just equal to VA over RA. It will give us 571.3 milliamperes, given that RA is just equal to 6 ohms. So after that one, we could break down actually RA. We could bring back R2 and R4. Now, RA is just equal to R2 plus R4, meaning to say R2 and R4 are in series with each other. So meaning to say, whatever the current that is passing through RA is just equal to the current passing through R2 and R4. Hence, our I2 and I4 is just equal to 571.3 milliamperes. Now, we could solve for V2 and V4, the voltage passing through R2 and R4. So, solving for the voltages V2 and V4, we have V2 I2 R2 and V4 I4 R4. So, V2, that is just 571.3 times 10 raised to negative 3 amperes times 5 ohms. It will give us 2.857 volts. And for V4, that's I4 R4, it will give us 5.713 times 10 raised to negative 3 amperes times 1 ohm. So V4 is just equal to 571.3 millivolts. In summary, we could now have this answer for letter C and for letter D. So that is now how we solve for our current passing through each resistance and the voltage across each resistor in a given series parallel combination configuration. We know that in a given circuit or in any appliances, there must be an EMF, there must be an electromotive force, wherein there should be something that is doing the work. So it must exert power, and that is power equal to the current passing through a resistance times the voltage being supplied by our power source. And then the unit of our power is actually in watts, or capital letter W. It is the time rate of which that EMF is doing the work, and electrical power is the rate at which the charge is forced to move by the voltage. How much power needed by our voltage source in order for our charges to move. Now, since we're dealing with motion, and then we are dealing with materials that are not perfect, and we want also to limit our current, so we are limiting the motion of our charges. Meaning to say, it is as if there's friction. If there is that friction from our understanding of general physics 1, it would tend to limit the speed of our particle. So it means that after limiting, it will actually generate heat. If you rub your hands together, it will create heat. The same thing with our circuits. If you're limiting the amount of current or amount of charges that is flowing, then it will actually generate heat. It will generate heat through the resistance, and the power dissipation in resistance will be better if we will, from our electrical power that is equal to IV, it will be better for us to express it in terms of resistance. That's why our power now is just equal to I squared R and or V squared over R. And heat is being developed because of this resistance. Let's have an example for this one. Example number 7. It will be very easy. This is just direct substitution. How much power will be used by a toaster with a rating of 10 amperes and 220 volts? So, P is just equal to IV, that is just 10 amperes times 220 volts, yielding power that is just 2.200 kilowatts. Lastly, number 8. Calculate the power in a circuit where the source is 100 volt, produces 2 amperes in a 5 ohm resistor. So, our focus now is the resistor. How much power will it absorb? So, P is just equal to I squared R. So, that's 2 amperes squared times 50 ohms, giving us 200 watts. For our practice problem, we now have this kind of configuration. For the given circuit, solve for the following: the equivalent resistance, the current passing through each resistance, the voltage across each resistor. So we now have the givens Vs, so 18 volts, V1, 150 ohms, R2, 300 ohms, R3, 600 ohms, and R4, 100 ohms, with your answers already given. So just be mindful with my units. I use there for the current all in milliamperes. Okay, please be careful with the units. So yay, we're done with basic electronics, part 1 and part 2. We have attained all our goals that we have discussed here. Now, as for our reflection, we take a deep breath. You just have finished understanding the last part of basic electronics, the last part of general physics 2. The study of electronics has paved way too many innovations and technologies that we could never imagine. That the impossible can become possible. In going through with this journey, innovators like Elon Musk experiences difficulties in reaching what they have achieved now. It is not easy and sometimes painful. It takes a toll on someone. Now, as an Athenian, are you willing to take the risk, the possibilities of being in pain in reaching your goals? I hope you could reflect on this one as we have finished General Physics 2. So in behalf of all general physics teachers, we congratulate you in finishing general physics. I wish you good health and good luck in your future endeavors.